All right, we're going to go ahead and get started. Thank you all for joining us today for this webinar. I'm Jen and I work with the 2GM team here at OCI. We are really excited for our special guest presenter, Asim Jiva, here from Amazon, the Software Development Manager. And joining us today from the 2GM Groovy and Grails and Micronaut team at OCI is Alvaro. They'll be giving us a tutorial demonstration on the most effective ways to reduce latencies with Micronaut and Amazon Corretto. Thank you again for joining us. And with that, I will go ahead and turn it over to Asim. Thank you.
Thank you very much for the introduction. Again, I'm Azim. Let's get started. Just a quick overview. We're going to talk about Corretto, what it is, how it came up, and why Amazon is investing into it. We'll discuss Shenandoah and why it is a great way to reduce latencies in your application, and talk a little bit about what GC latencies are. Transition over to Alvaro, who's going to give an overview on Micronaut, a demo, and we'll have some resources for you to take a look at after this session. All right. So, what is Corretto? Right? What is Corretto? Corretto is a downstream distribution of OpenJDK. OpenJDK is what's considered the open source implementation of the Java Platform Standard Edition, right? J2SE. OpenJDK is the actual project where the source code lives. They started providing binaries. We are a distribution of that. Right now, as of today, we provide two no-cost, long-term supported releases, what's traditionally called an LTS release, Corretto 8 and Corretto 11. They correspond to their specific OpenJDK releases. Corretto is a reliable build of OpenJDK. We provide long-term support, at least for Corretto 8 until 2026, and it's TBD if we extend that. And we run it internally on thousands of production services. It's in-house. We run it. We test it. It is something that is used by all of Amazon to run our business. And we think that's important because, one, it gives you the confidence that these are actually tested in production and being used. But it also means that we stand behind it and it can provide our commitment to provide performance, security updates, at least on a quarterly basis, on the same day as OpenJDK release. And it's all no cost. We're firm on never charging for Corretto. In addition, it's a pure drop-in replacement for Oracle JDK. You can transition from the same version. We hold all of the APIs compatible. It's tested and certified by the TCK and available on Linux, Windows, macOS, Docker. We now have an Alpine build, 64-bit, 32-bit, and you can check it out by clicking on the link. So you may ask, well, why Corretto? Why did we do this? So Amazon has 14 leadership principles. What I believe is one of the most important is customer obsession. And 90% or more of the Corretto roadmap is driven by customer needs. And we treat both internal and external customers the same. We are, again, very customer obsessed. So back in 2016, Amazon found out that we use Java heavily, and we discovered that very quickly that it's not easy to rely on a binary distribution. We have thousands of applications running in production, and the ability to fix bugs quickly is important. I'll give you a really good example. This is a few months ago. One of our customers came and filed a ticket for a crash in the VM. It was called a C-free error, so it was within the JVM itself. My team investigated, found the fix, tested it, built a new binary, and had it to the customer within a few days. This solved their problem, and we took that patch and we upstreamed it. So this is something that we find very critical to running Amazon, and we will do the same for all of our customers. And then, because now we are able to build from source and can regularly provide binaries, we also are working on performance improvements. Again, like I mentioned, fixing bugs. All of this is upstream. We try to keep Corretto as similar source-wise to the upstream repositories. So what enabled the Corretto adoption? Like what was the driving factors? I mean, besides the ability to quickly fix things, we needed the ability to just have it drop-in compatible. Assuming there's nothing that's non-OpenJDK, you can take the Corretto, drop it into a replacement VM, and it will work. Within Amazon ourselves, we have automated deployment pipelines to really roll out across the entire fleet very rapidly. It's like any other deployment for us, and it allows us to upgrade Amazon very rapidly. Again, upsides are a lot of performance goodies. We backport a lot of changes. We do big fix bugs. We keep our repositories available, open source, so you can go look at the changes. My team works on all sorts of different platforms, support for things like Alpine, the Docker, and what have you. All right. So you may ask, well, why do we have an external binary of Corretto? That's great for Amazon, right? But Amazon, for one, we've been shipping OpenJDK on Amazon Linux for some time now. So this is not something that we're new at. We just kind of expanded the scope. Back a while ago, now I guess 2 years, Oracle announced the end of public updates for the Oracle JDK 8. And they moved to a much more rapid 6-month cadence with Java 9. And what we found is many of our customers still need that supported JDK 8. They really needed a long-term supported release. And again, being customer obsessed meant that we need to answer that call, and this is where Corretto is born. And we're dedicated to keeping Corretto free, available, and until at least 2026, and possibly further as the time approaches. So again, this is why it happened, and this is what we're trying to do. All right, so you may ask, well, great, how do I get support? So first, it's no cost. We provide security patches quarterly. We had a release on the 20th of this month, same day as OpenJDK, and dozens of other downstream releases. So we're active on GitHub. If you go to our GitHub repo, it's a link. There'll be a link in the resources. You can file a ticket, submit a PR, work with us. If you really need that hand-holding, you can, of course, file a ticket through AWS Premium support, and they'll route to the right customers. Again, we're very customer obsessed, and we really want you to have a good experience with Corretto. All right, you say, well, great, you do all this stuff. How do you actually collaborate with the upstream and the community? So one of the things is that we all upstream everything. We very rarely keep things around, and anything that is not merged, most likely is just because we're still working on it. But again, we try to keep it as similar as possible. We work with Red Hat and the rest of the community, Oracle, others on JDK 8, 11. My team is now starting to work on Shenandoah. We had our first patch accepted a few weeks ago. Working on other patches. And you can see, we're active on Twitter. If you use the hashtag #Corretto, one of us will surely see it and comment on it. That's how we collaborate. If you look through the OpenJDK aliases, you'll see my team is quite active in a number of areas: compilers, GC, security, runtime. All right, so great. That's Corretto and what Amazon is dedicated to working on. But how does this help with your latencies? Corretto has support for Shenandoah. We've merged it, taken the OpenJDK sources and enabled it. And this is something we'll talk about why Shenandoah, what's new about it, why is it something that you'd be interested in. All right, so first of all, what is Shenandoah? One, it's a new collector, garbage collector. It was developed by Red Hat and made freely available. As I mentioned earlier, we're collaborating with them. And you say, well, what's the advantages? We have G1, we have CMS, which is soon to be deprecated, but still available. We have Parallel. What does Shenandoah provide? So the one thing that Shenandoah really attempts to do and provide you is pause times that are under 10 milliseconds. That's the kind of the goal. And it has a number of features, which I'll discuss, of how to get there. So again, low latency, low pause times. And your pause times are not proportional to the size of the heap. While many of the other collectors, if you have a small heap and lots of processing power, you can keep pause times reasonable. But as your heaps grow, and it's not uncommon to have 30, 40, 50, 60, hundreds of gigs of heap, depending on your application. There are some disadvantages for now. Your throughput will suffer, although we have in-house seen anywhere between 0 and 15%. Again, it'll depend on your specific workload. And also, you'll need more free heat. It is a single generation collector, and the way it works requires a little bit more headroom. Again, if you're willing to make these trade-offs and deal with from an application level, you can get very good pause times, P99.9 of under 10 milliseconds. All right, so you say, well, how does it do this? This is great, right? You want to actually do this. So I'm going to very briefly talk about the various phases with a focus on the where the locations where it actually causes pauses, because mostly Shenandoah is concurrent. It's what makes it a concurrent collector. So there are 4 specific areas where the application itself, the garbage collector itself pauses the immutary threads of the application. One is the init mark, the final mark, the init UR, and the final UR. That's the update references. So when you're doing an init mark, the phase that you need to actually stop the application. So this is the first phase. It actually initiates the concurrent marking, which goes forward. It prepares your heap and applications for the concurrent marking, and it scans through the root set. This is actually the first pause. It's the most dominant in the root set scan, and the duration is dependent on the root set. We can discuss what that means, but for now, that's what it's dependent on. And the concurrent mark now is running alongside your application, which is a little bit different than other collectors. And its duration is dependent on the number of live objects. So again, more live objects. But since it's running concurrently, it's not causing your application to pause. And it's possible, though, during this phase that your application will allocate new objects, and most likely. So the heap occupancy is going to go up during this phase. And this is why you need more free heap because of the way this works. Once that's done, you'll hit the final mark phase, which finishes all the concurrent marking. It drains all the entire queue, rescans the root set again. So again, this is the heavy phase here. This is the one that takes the most time. It figures out what are the regions need to be evacuated, collected. It may even do some pre-evacuation depending on where they are in the route. And it prepares for the next phase. So part of this can be done concurrently, but for now, this is the big chunk of work. This is the dominating pause time for your application. And again, going back to the original, this is why you need more free heap. And then concurrent, once that's done, you concurrently clean up. This is where you actually clean up the objects, remove the data, and evacuate to other regions. So you're compacting a little bit. To run alongside with your application. Again, your application is free to allocate and run and run alongside it. You have now a smaller update, small phase where you pause again. Again, it's very small. And this is why you're seeing under 10 milliseconds, right? These are very short pauses. It again updates all the references, and it does nothing except to make sure that the GC and application threads have finished the evacuation. Again, very short. It's actually the shortest of them all. And now concurrently, you're going to walk over the heap, the update references portion. and it updates all the references to the new location where the objects have moved. Again, one more pause, the final update reference. And this is where you make sure that the objects are all in the right place. And it points the objects in the new locations to the location that they moved. You clean up, and your application is active. And that's one full cycle. So this is kind of like how the Shenandoah works, very high level, and some comments there. All right. So you may say, well, how do I limit some of my pause times? Again, it's all application dependent, but in general, Shenandoah's pauses are very much dominated by the root set operations. How many local variables you have, how many references you have in generated code, internal strings. If you have a lot of class loaders and references to them, especially static file references. JNI, JVMTI, those are always a cause. So in general, the larger your root set, the longer the pause times. While there are ways of kind of finding this out, I still recommend that you focus on writing good code, clean code, rather than trying to target for pause times. Write good code first, worry about the pause times afterwards. So this is the overview, and this is how Corretto and Shenandoah works. I'm going to hand this over now to Alvaro, who's going to talk about Micronaut. So Alvaro, I'm going to stop sharing here and hand it over to you.
All right, good morning, everybody. Good afternoon, good evening, depending on where you are. My name is Alvaro Sanchez. I'm part of the Micronaut team at OCI. And I'm going to give you a little brief introduction about Micronaut, and then I will do a little demo of a Micronaut application under load using Corretto and OpenJDK, and we will compare them both and see some results. Micronaut is a framework that was created in, it was first published in 2018, the first release, and it's a general framework for the JVM to create microservices and serverless applications. We call it natively cloud native because it's been designed from the ground up with the cloud in mind. So we have embraced the 12-factor patterns so that you can build microservices for the cloud. And natively because this is not a 10-year-old or a 15-year-old framework where we had to carry over many decisions. So we start fresh from scratch with this goal in mind. It's ultra lightweight and reactive. So it uses Netty as a reactive stack under the covers. But your code can or cannot be, it depends on you whether you use reactive programming or not. So you can use blocking operations, that's totally fine. Or if you prefer, you can benefit from a fully reactive stack if you want to do that. And we also support like traditional runtimes like servlet APIs. So you could deploy this in a traditional like a Tomcat Jetty container. One of the key differences of Micronaut versus other frameworks for the JVM is what is called AOT compilation. AOT stands for ahead of time. So at compilation time, at compile time, we pre-compute the majority of the framework infrastructure. So for instance, the dependency injection engine, the AOP engine, everything that needs to be produced by the framework is pre-computed compile time. So that at runtime is much faster. So there's no runtime reflection, there's no proxy generation on runtime. We don't do class path scanning. We don't have to visit every single jar file, every single class, every single member of a class to look for annotations at runtime because we do that at compile time. So the result is that the start time is insanely fast. We're talking about sub-second startups, and much lower memory consumption because, reflection takes a large amount of money, and we don't use reflection at all. So it's started to start, and it consumes less memory. In an era of cloud applications, serverless function, where you're built by the utilization of the resources, I think those two benefits from the framework may make a big difference for some people. You can use either Java, Kotlin, or Groovy as your application languages. The three of them are fully supportive. There is actually Scala support on the roadmap and actively being worked on. In terms of build tools, you can use Maven or Gradle. We support both. We have plugins for the both build tools to make it easier for you to create applications. Speaking about the cloud, we support the majority of cloud systems and integrations, like the major cloud vendors, Amazon, of course, but not only, also Google, Azure. We have integration with Consul, Eureka, Zipkin, Tracing. So, the most popular systems are already supported. In terms of data access, you can use different options. One is Micronaut data. Micronaut data is the data access solution for Micronaut applications. And Micronaut data follows the same principle as Micronaut, in which you implement repositories, and you can use JPA. But unlike other implementations, like for instance Hibernate, in Micronaut data there is no reflection at all. So it's the queries are pre-computed at compile time, so that at runtime the only cost is to actually execute them. With Micronaut data, you can use either the JDBC flavor or JPA if you prefer that. And also there is a generic support for all the data stores, like NoSQL, DocumentDBs, MongoDB, Redis, GraphQL, etc. Cassandra as well. So there are integrations for all those platforms. You can get started in two ways. One is visiting Micronaut Launch, which is a web application that will give you, a blank application with all the dependencies and the necessary code to start with coding. You can select the features you want to be part of the applications, and depending on those that you select, you will get the appropriate build, the appropriate configuration elements that you need to have, so that you can start coding right away. The alternative to using the website is to use the CLI. So there is a CLI to create applications and to scaffold some files like controller or test, things like that. And the result is the same. You will end up having like a blank application with all the dependencies and configurations. Speaking about AWS, we fully support AWS, of course. You can write normal applications. And by normal applications, I mean applications that have a controller, services, etc. You could deploy that on EC2 or even Lambda, or you can write a serverless function. A serverless function can be deployed on Lambda, And for that, you could use either one of the Java runtimes, in which you will end up using Corretto 8 or 11. Or you could package your application using RouteVM to produce a native binary, and then deploy that as a Lambda custom runtime. In this case, the call startups for your function will be like really smaller, in the milliseconds. And there is also support for Alexa to write Alexa skills. You can deploy Alexa skills as Lambda functions as well. There is support for using the SDK v1 and v2. For instance, in the case of the SDK v2, there are pre-configured clients for you to use, like S3, DynamoDB, and a few others, like the most popular ones. And you can easily write your own. Micronaut is also certified to run on Corretto, so we test the own Micronaut code on Corretto, and we do that on the major platforms they support. Currently 8 and 11, and we'll plan to do that with 15 once that's available. So that we make sure that not only the Micronaut code, but also the hundreds of tests we have, which are functional tests, run well on Corretto, and that will give us confidence that when our users deploy Micronaut applications on AWS, they won't have any issue at all. So the demo, what I'm going to show is a sample application. It's using Micronaut data JDBC. That's the link for you if you want to check it out. But it's really simple. It's like a hello world, but a little bit more complex, because I didn't want to just demo a simple hello world, but using a database. Although in this case, the database is an in-memory S2 database. And I will run load tests with both OpenJDK 11 using G1 and Corretto 11 using Shenandoah. There is an initial warm-up period where I will throw like 10,000 requests per second using 10 threads and 500 connections within 20 seconds to allow for for optimizations of the Git compiler and so on. And after that, I will throw the actual load during 60 seconds. 50,000 requests per second during 1 minute. And this is all happening on my laptop. So yeah. The versions used for OpenJDK is 1109. And I'm not using any modifier at all, so it's plain Java -jar. In the case of Shenandoah, is Corretto 1109. And in this case, the only flags I'm using is the ones that are required to enable Shenandoah. Shenandoah has other flags to further customize how the garbage collector works, but I'm just using the defaults. I'm also using the defaults in terms of heap size, like a min and max, so we'll see how that behaves. I'll switch to the application in the terminal. So before I actually run the demo, a little bit explanation about the application. So a Micronaut application is a regular Maven or Gradle-based application with the standard directories. There is a main class that you can use. And then this particular one has integration with a database. We have the entity. In this case, is a JPA entity. Or actually, it's a Micronaut JDBC entity mapped with JPA annotations. So we allow you to use JPA annotations, or you can use the Micronaut ones. So that's up to you. In this case, I use the JPA ones. So this is this represents a football team, or soccer team if you're in the US, with a couple of fields, and then there is a repository. You may have seen this approach in other frameworks. The difference here is that this interface is going to be implemented, or the implementation is going to be generated at compile time instead of runtime. And then we only have to specify here the class of the entity and the primary key, and then the dialect of the database we're using. And finally, I have a controller. So Micronaut REST controllers are either annotation based, like this. This is probably the most common approach. But there is also a programmatic API for routes, where you can map controller actions into particular routes with an API. In this case, I'm using the annotation approach. So there's going to be like a /themes endpoint that will map to this final method here, and then /theme/number, which will map to this action here, and we are using the repository. So the repository, remember, this is the interface, but you get for free, like the most common CRUD operations, like save, delete, maybe update, blah, blah, blah. So I could run this application. Can I do that? Corretto run. Demo time, of course. That's probably an existing instance. Okay, started completed in 1.6 seconds. And then we can make a request. Make this bigger. Sorry. 08080/themes. Right. And then the one, so this works. What else? So we can write tests really easily. Let me show you that. I have a JUnit test file, the test here. By the way, when I ran this application, you could see we had a couple of entries on the database. I'm using this application event listener to insert a couple of elements when the application is running. This is also a good excuse to show you, for for instance, the annotations we use for the DI. We use JavaX inject annotations. So singleton will make this class a bin. And then the conditional bin support in this case is that I'm making this element only available if the environment is not test. Why? Because during the test environment, I will control the fixture data that I want for my tests. So I want to have it to start from a clean database. This is a JUnit 5 test. We provide you with a Micronaut test annotation. You can write either JUnit 5 or Spock tests. The notation is the same and the behavior is the same as well. Using Micronaut test, you will get the embedded server to be run on a random port, and then the test class itself will become a bin, and you can inject other bins and call method calls on them. So this is not a unit test. We're testing the real thing. We are running the entire application, and actually running the application involves because we are using H2 and the defaults. So Micronaut will create the schema for us. We'll initialize the database. We'll do a few things. So if I run this test, right, we can see the test execution is 212 milliseconds. This is not counting the time to start the server. But if you compare with the time it took to run it, which was 1.6, so it's around 1.2 seconds to start the server, and then all the tests can run really quickly. And this is a functional test. So because the feedback is so quickly, I mean, you could write unit tests, of course, if you wanted to, but it's really comfortable to write functional tests and test your application without having to mock a lot of bins to get your test working. Okay, so I will get into the running of the demo. So first of all, I'm starting with OpenJDK. We're going to see in Visual VM the progression of the heap size. So here we have finished the warm up, and then we are starting the actual load test. You can see the footprint is something around 30 megabytes, 20 something, right? Those are the typical spikes of G1 garbage collector, where the heap use keeps growing until it executes a GC. We see longer increases in garbage collection here. So that's probably a long pause happening. So this is the typical graph for an application that you might, I think this has finished already. Yeah. So Yeah, the heap used was between 30 megabytes and 200, more or less. So it's kind of consistent. I'm cooling down during 30 seconds to my laptop fans to cool down. This is the Shenandoah applications. Those are the arguments used. I'm also logging all the GC activity to a file, which I'm not using today, but I have run this before and have analyzed the log files with tools that produces charts, and we'll see them in a moment. So we're in the warm-up. The warm-up is finished. The first thing you can see is the heap utilization is much bigger, like several times bigger. But this is expected because Shenandoah is a single generation collector, as opposed to, for instance, G1, where I think we can see in Visual VM, if you have the Visual GC plugin, you can see the different spaces for the collection. Well, this is for the previous application. But Shenandoah is a single generation collector. Footprint varies, but the minimum is 166 megabytes. So, okay, this has finished already. So you can see heap utilization is much bigger. This is the downside. So if we go back to the results, if we actually I measured the latencies on both the client side. So I'm using WRK2 for load testing. Then exported all the output to terminal in a format where I could produce histograms. So this is the histogram of both OpenJDK in blue and Corretto in orange. And you can see the latencies using Corretto from the client side are much smaller. So not only the average is smaller, but also the maximum is smaller, and the majority of requests are served between 10 and 20 milliseconds versus like 10 and 60 milliseconds for OpenJDK. So this is the latency that the client experiments. So the amount of time to receive a response. Heap statistics. This is what we saw live. OpenJDK G1 versus Shenandoah. So we're talking about peak usage of less than 200 megabytes versus 3.5 gigabytes. So several times. So if you can afford to have the memory, you can benefit from the lower latencies. So internally, those are the numbers of the GC performance. This is G1 with OpenJDK, and those are the garbage collection activities. The average post time is 1.4 millisecond with a maximum post time of 4 milliseconds. So this is time where your application is not running because there is a pause where the collector is running. And the majority of pauses are between 1 and 2 milliseconds. This is the histogram of the duration time range. If we compare that with Shenandoah, we can see the average pause time is like 1/4 of that of G1. The maximum is a little bit bigger, but it's not really important because that could be another case. Because 94.23% of the pauses happen in less than 1 millisecond. So it's really fast. So this is the benefit of this, and the client side latencies as well is the benefit. And then comparing, for instance, garbage collection pauses side by side, the pause time of G1 was the total time was like half a second. So half a second where your application was not running versus 26 milliseconds. And then both algorithms have a pause time where the garbage collection running exclusively, and a concurrent time where both your application and the garbage collector are running. So you can see, the amount of concurrent time is similar for both, but the difference is the pause time. The pause time is extremely low with Shenandoah. So those are the numbers. I hope you enjoyed this demo and the introduction about the framework. Before we get to the Q&A, we have some links and resources. Jen, you may want to comment on those.
Sure. So here is a list, as Alvaro said, for some community resources for Micronaut, anywhere from following us on Twitter to where to launch your first Micronaut application, as Alvaro showed you earlier in the presentation, Micronaut launch, to some great learning resources. There's documentation, there's guides. We post everything that we've published on our blog, as well as information on the Micronaut Foundation. And then also we've got some resources for Amazon as well, where you can find information on Corretto and Shenandoah as well, and following them on Twitter with the hashtag Corretto. And we'll be turning it over now to David with AWS as well, and he's going to help us go through some of the questions that you guys have sent over. So David, thank you for joining us, and I will let you give these guys some fun questions to answer.
Thank you. Yeah, my name's Dave. I've been at Amazon a little over 7 years. I'm an advocate on the developer tools team, and my pleasure to be here today. Thank you, Azim and Alvaro. Lots of info, lots of stuff to unpack. I always love a live demo and some data too, so I super appreciate that. We've got a couple questions here. I'll post them in the chat. So first question, is Shenandoah available in Corretto 11?
Yes, yes, it is. If you download the release that we just released on the 20th of this month, 1109, it's available.
Right, and I know that was the one that was shown in the demo too.
Right, and it's on Linux, all the supported platforms that Shenandoah has, Linux, Windows, and Mac.
Okay, and I just put the link in there too as well. All right, another question. can I build Graal VM native image AWS Lambdas with Micronaut?
Correct. Yes. You can build native image operating platform, of course. In the case of Lambda, we have a nice integration with the build plugins. The Gradle plugin is already released and allows you to build the function zip file that you need to upload to a Lambda custom runtime, and then you can deploy that to using SAM to local deployment, or you can use the AWS CLI to deploy that to the cloud, and the build process will take care of producing the binary on an Amazon Linux container, and then installing GraalVM inside, executing the native image binary to produce the binary. So it takes care of everything to produce the function.zip. And for Maven, the integration is going to be released with Micronaut 2.2, which is expected to be out in the middle of November.
Okay. And I think nobody has had a problem being on mute so far, so which is like perfect to do a webinar like that. So thank you. Let's see here. Another question we have. I'll paste it in. So got some questions on what were you using with the logs when you were showing that live demo, and you were using, so you were graphing everything and you were simulating a large number of requests. Got some interest in that tool.
Yeah, so this is Visual VM. This is coming with OpenJDK. So it's part of your JDK installation. And this is an open platform, has the support of plugins. In particular, Visual GC is a plugin, but this plugin doesn't support Shenandoah yet. So, so yeah, this is Visual VM. I believe there are other commercial tools from Oracle, like Flight Recorder and things like that, but I didn't use them. So Visual VM should be available from OpenJDK. And during the demo, I did write all the GC activities to the log files, and then I used a website called I think it's gcec.io that parses your GC log files and produces the charts that I showed.
Okay, excellent. I got, all right, we got another question here. So do I have to build with Corretto in order to deploy using Corretto?
No, you don't. You can just build with whatever toolchain OpenJDK adopt. It doesn't matter. It all ends up being class files, which then are run with the VM. So it's
okay. All right. Question. This one just came in. Does GraalVM support Apache Commons libraries like collection utils?
It does support some of them. It's not the case that GraalVM supports them or not, but it's the case of whether those libraries use reflection or not, and if they use reflection, whether the exceptions have been configured properly, so that the native image binary can produce the closed world version of the application. For instance, if we talk about the SDK v2, one of the clients the SDK v2 supports is Apache Client. Apache Client uses reflection heavily, but we had as part of the Micronaut AWS integration, we produce native image properties with all the discussions so that the Apache client works correctly. So I don't remember having used those libraries in particular, but it might be the case that one needs to produce a native image properties with the initialize at build time, and then whatever packages that are using reflection to be part of that configuration file.
Got it. Question for you. Can you set the Shenandoah JVM flags in Lambda? And are these flags useful for faster startup?
Can you set JVM flags?
This would be with the Java 11 platform set in Lambda.
I'm not really sure about that, to be honest, because I think you can. So in the Java 11 runtime, you upload the jar file. That's where your packaging ends. And then I believe using the AWS CLI or the UI, you can specify flags. But I'm not really sure right now if you can specify JVM flags as part of the deployment.
I mean, Lambda supports Corretto, and if you can set the flags, then yes, you could use Shenandoah.
Yes, I mean I'm pretty sure you can, but
right.
Yes, I wasn't sure right now.
Got it. All right, we got 1 minute left. So depending on how fast I got another question or two. Is Shenandoah the default GC for Corretto?
No, it's not. It's still G1. We didn't make the change. We just made it available.
Okay.
Is the same for OpenJDK.
Right.
Got it. And all right, this will be our last one. What are the options to deploy Micronaut applications on AWS?
So the options are you can package your application as a Java file. You can use or build plugins for Maven and Gradle to produce the artifacts and then upload to, if it's a jar file, it's a runnable jar file, so that you can run that with Java -jar on any situations, or you can upload that to any Java 8 or Java 11 Java runtime for Lambda, and you can package your application as a native image as Lambda custom runtime, in which case our build plugins will produce the function zip file, which will contain the launcher script and the binary.
Got it. All right. Well, thank you, Jen. I'll pass it over to you.
All right. Thank you so much, David, for doing that for us, and Alvaro and Asim for presenting. And yep, thank you guys, and we'll see you all next time.
Thank you very much.
Bye, everyone.